Okay, see, we will continue talking on rudders, or you can say rudder and control surface. In the last lecture, we actually I spoke about how we, describe a geometry of a all movable rudder, and also in terms of CLCD, how you basically can end up getting the net forces, torque, whatever you require. The two things are necessary. One is so called YR etc., that is basically the rudder force needed for maneuvering equations. The other is for rudder design itself, the torque and moment that comes in the rudder stock. Okay. Now, today initially therefore what happens, we require to make some estimates. So, as I was telling last class, I will tell you today about some empirical, semi-empirical formula about how we can find out this rudder forces and the related quantities. So, initially I am going to say even simpler than what we have done in CLCD. See, rudder force we have defined last class in terms of basically CL, CD, etc. Okay, we resolved it, but not going even to that. There are some even simpler semi-empirical formula which would be very useful to make a quick estimate for other forces, etc. Now, basically this force will depend, as we know, obviously it depends on, well, CL, we can say rudder force or CLCD is the same thing, depends on cross in fact on these two depend. Of course, the force will depend on rudder area, it will of course depend on geometry. Now, this geometry primarily will be influenced by what is called aspect ratio, it is very important. Span by chord. Taper ratio, sweep angle. Essentially, we discuss this, that is how it is tapered. Okay. It will of course depends on V square, it will depend on V square rho and angular attack alpha. We all know that. Why I wrote this? Because see, instead of going to CLCD, I can simply write rudder force, where rudder force may be the force in the normal direction to rudder, as a function of some constant into rho into AR into V square into, now this is nothing but actually some force, right. Why I am mentioning this? Because you see there are some, before going to CLCD form, which also I will mention a more detailed form, there have been some empirical formula based on just this very older kind of formula, where you have just a constant into this, so you can find out kind of a rudder force. So, one of this old formula, for example, says simply, one of this old one, it says simply that it is 577 based on AR V square sine in Newton, when AR is area in meter square, V of course is speed in meter per second, and when you do V, it should be the fact that the water flowing past rudder is of higher speed because propeller racing it. The rudder will be always behind a propeller typically. So, the V that comes into rudder is usually higher. So, this in this formula one have to use V equal to 1.3 into V ship if it is a rudder behind a propeller, a single screw ship, and if there is a centerline rudder, this is for or one could use 1.2 into V ship for center line rudder behind twin screw. Okay. So, this is one of the formula. Why I am mentioning that, you will find out that you can very quickly, very easily, find out the force, and then I will mention about the moment and torque part. The another formula, this one formula, another formula. If what? No. It's true. This is why I said rudders behind propeller. It can be single screw, twin screw, as long as if you have the rudder behind the propeller. But there are ships where rudder is not behind propeller, they are twin screw but central line rudder. See, there are ships there. There is a propeller here, there is a propeller here, but the rudder is here. This is what we call central line rudder behind a twin screw ship. It is not necessary. See, what your question is that even in twin screw I will have rudder behind propeller, but no, we are talking of that design where there is a central line rudder behind twin screw propeller. Okay. So, it is not mandatory that you must have a rudder behind a propeller. Another formula is, it says, this is all like sequential. This is much older. The next one is little more newer. It says 21.1 AR. All of them. See here, if you look at the, I will just mention that. Okay. I equal. See, the question is like that, when you do a semi-empirical formula, what you are doing? You are actually measuring, or you have collected lot of data of forces. You know the force will look like a constant AR V square into some kind of delta sine or otherwise delta R. You try to find a constant. So, in this formula, what they have done is that this V here, if you want to apply, you have to use V as a V true ship, because that factor whatever has been already embedded in this constant essentially. Okay.
So what happens to the rho?
Rho has to be there. Yeah. Yes. Rho has to be there. Here, no. Sorry. No. Rho actually here. Rho is taken inside that. Right. Rho is not, because rho is taken inside this all. Rho is around 1.025. So it's already taken inside that. See, actually speaking, this is not a non-dimensional, this is a dimensional. This number, that's why these dimensions are mentioned. You have to apply this dimension only. So this constants actually includes that rho and other factors. It will not be the same one if you use another unit, basically. Okay. Now, if you know this force, that this. Let me just tell you one thing, that. Suppose this is a rudder, some rudder here, this is a stock here, the force acts somewhere here, right? This force is acting here, Fr, we are calling that. Now, there is going to be a torque T. Now, quite often there is going to be also a moment M. why I am mentioning that, see, essentially you want to know this moment at this location on the stalk. This is the stalk. This is not there. This is basically the stalk, or this red line, if I were to plot this. And you want to find the moment about that. So, yesterday we mentioned there, no, in terms of lift and drag also you can find the moment about the root section, but actually here if you take the contribution of T and M, you can also get this moment, and this turns out to be, it turns out that moment here M dash becomes equal to half of, let me just write it down so that we can, what it means is, see here, this about this root section I find the moment, but this is not acting on the stalk, so there is a torque on this. So, an equivalent moment can be found out at this point, at this location, by combining the two. This is basically based on pure structural mechanics. The why I am mentioning is because from the design point of view of this stalk, the max stress is maximum, and you would like to know what is the bending stress coming. We will do a problem of that later on. So, in order to do that, what I need to do is to estimate Fr. Once I know the Fr, and of course I have to also estimate these distances, that is, this is my center of pressure Cp. I need to know the location of Cp, that also I will come to that, this formulas for this Cp later on. Once you know that, you can find out the moment coming, and of course once you know Fr, you can also resolve these forces as we mentioned yesterday, how you can determine ydr, mdr, etc. There is a Hull properties. Okay, these are two simple formula. I will mention a slightly more complex formula which is more used nowadays. This formula will be, that formula is in terms of CLCD. Remember, these two formula, there is no CLCD, it is much older formula. Now there is a newer formula for getting CL and CD and CM. Remember that yesterday we mentioned that we actually have, in terms of this, all forces, moment, etc. could be found out. We discussed that yesterday fully, right. Now these formulas are not talking of CLCD, etc. They are simply assuming them to be the function of alpha is embedded from the experiment. But later on what has happened, when people started using, remember this, before I go that, many you would see it even now, many river boats, you will find out the rudder is simply a plate, just a plate, rectangular plate. If you go to country boats, you will find some kind of wooden, just a stick like that sometime. The person is just shifting. Okay, so these formulas evolved at a time when there was not so much of discussion or so much of knowledge based on the aerofoil section was available. That is why there was no concept or use of CLCD. This what CLCD started coming more when it is actually having an origin from aerospace engineering. When you are begin to think a lifting surface, begin to think of an aerofoil section or hydrofoil section, etc. So later formulas all realize that you will get much better rudder performance if you use aerofoil section of some form. Then you can get, see, if you take aerofoil section, you get for the shape also and lift and also angle of attack. Actually, if you flat plate also, if you look at angle of attack, just a flat plate, you will get a lift, but not so much. And those formulas are based on similar kind of idea. Now later on this CLCD came, and as I said yesterday, we kind of expressed all the forces in terms of CLCD or LD, etc. So now these present formulas are all the more later formulas try to tell you, estimate CL and CD, etc. all this by some empirical formula. So this is what I am going to write it down. For example, CL is now here, this is meant for, again before I do that, meant for the geometry that I showed yesterday. Remember, this is the kind spade rudder geometry I showed, fully movable. This is the line there, this is root section, tip section, the tip chord, this is a swipe angle, etc. We plotted that yesterday in terms of these parameters, in terms of essentially what is important, as I mentioned before, aspect ratio, this by that, effective aspect ratio, because this is not exactly same. So, you can take the mean line, or you could take S square by area. If you call this to be span, this to be area, span square by area becomes effective aspect ratio. That is extremely important. Aspect ratio is extremely important. Sweep and taper angle can be this by that, can be called taper. Okay, how much it is tapering, these parameters. So, these formulas are based on those parameters. So, this here CL is written as, maybe I will write in a newer page because it is a longer formula. Let me preamble this as that more recent formula for estimating rudder forces, so that we know that here it says CL, it is DCL. Now, there is another problem will come. This of course everybody knows, it will be this, but the essential thing is the correction term CDC by A alpha by 57.3. The alpha is the angle of attack in degree, that is why this divided by 57.3 degree comes in. Alpha is, I will write it down. This is one, then BCL by D alpha. Okay. This is equal to, this formula is going to be important, we will see it afterwards why so. See, I will tell you the important point here, DCL by D alpha. Okay, we have mentioned that yesterday, if you recall, yesterday we had this formula alpha versus CL, and this slope is DCL by D alpha at alpha equal to 0. If you recall, we had a approximate formula of YDR in terms of this. Okay. This becomes the most important characteristic actually at 0. The what is known as, this is what is known as slope of the lift curve at 0. Okay. Now, this is, so we know that A of course is effective aspect ratio. There are different way of defining this, but normally one define this to be span square by area. You know, because effective S by basically span by chord would be aspect ratio, this basically this, you know, this divided by this. What is the typical aspect ratio of a rudder, you think, of a ship? I am just in this discussion, let me just ask you, approximately how much do you think is an aspect ratio of a rudder? In which order? Is it 0.2, 0.3 or 1 or 2 or so? 1.3, 1.5, right, in that order. Okay. So, you have an idea, you keep this in your mind, because next class when we talk little bit about the ship hull derivatives, we will find out the ship can be treated as a lifting surface of very low aspect ratio, very low, because you know T by L becomes aspect ratio, but this is around 1.3. How do you get this? Supposing somebody asks you, I estimate that. see the T more or less this part will be same as the draft, and area you can take, as I was telling yesterday, to be about 2% of the like length into draft. So if you go by that, you will find 2% is 1/50th of that L, and L by T. If you use that formula, you will end up getting some estimate. Okay. So anyhow, you have an idea regarding that. I wanted to know that. See, of course, this we know the sweep angle. So we anyhow this we have already discussed yesterday. Alpha is angle of attack in degrees. In just still write. And this is CDC. This is important. This is what is called this CDC. See, there is an extra term that comes. This part everybody knows. There is no question. The problem is or issue is with this correction term. So this is what is called cross flow drag. Which depends on both tip shape and taper ratio. Now taper ratio is, I mentioned, this by this, this by this, okay, that is the taper ratio. This divided by that is chord at tip by chord at root. Typically, for example, this value would look something like that. If you the taper ratio was this cross flow drag CDC against taper ratio for different kind of tips. There are plots available, normally linearly varying. This is what is called fair tip. What I mean that what I want to tell you is that let me write it down. See, when you have an empirical formula, we must realize what is the meaning of the word. First of all, empirical, based on experience. So you have a formula where the form always has some scientific basis, that is point 1, but the unknowns you fill up from experimental data. So here CDC, this term, the form looks like that, but you don't know CDC. So people have done experiment, and it turned out that if you did experiment, CDC, the values are available. I am not putting the number that you can see in any standard textbook, but they seems to fit a linear variation with taper. Taper ratio, for example, here this may be 0.2. It can go up to 1. It cannot go up beyond 1. But most of the most ships rudder taper ratio is about 0.8, 0.9 in that order. So this is all like in any empirical formula. If you have the graphs available, you can always apply that. Okay. Having said that, now let's see the other part. Drag coefficient, that also you need. Now this was CL. So we have this drag coefficient CD. Let me just write CD. This is given by formula of that CDO plus CL square by pi AE. Now CDO is what is called minimum drag coefficient for the given section. For a given section, given foil section. For example, this turns out to be 0.0065 for, I will tell you again this. This is a very common section used. See, NACA 0. What is happening is that, again, people have done experiment. You would have chosen certain set of, well, these are called NACA profiles, that National Aeronautical, what is this, NACA, I don't remember this fully. This is aviation, something to do with this aeronautic and some aviation, So there are a whole lot of profile given, for which experiments have been done, for which the drag minimum drag is also available. So, you use that value in this formula. E is an efficiency factor, it is known as Oswald somebody is, as you can see, Oswald means based on a name. Again is available in literature. Okay, then moment coefficient about quarter chord, that is m c by 4. Remember, yesterday we defined this. This is moment coefficient about quarter chord. Why quarter chord? Because we haven't yet found the Cp. There will be formula for Cp also, and obviously you don't know the stock position. Remember, when you are doing these forces on a lifting surface. It doesn't matter where the stock is. Okay, so that's arbitrary. This doesn't depend on where the stock is. The flow comes this way, is going to give so much of lift. It doesn't depend on where the stock is. So that's why that is why these formulas are for geometrically determined point, not on like as you determine by design. So this is given something like, let us see this formula is big. I will just write it down from here rather. Again there is dCm by dCl at CL0. This is a graph. This is into, we will write here, into this minus half CdC by A. Maybe I should not write this too much, because this is all standard formula. Again there is a formula available for moment about quarter chord in terms of dCm by dCl, dCm by dCl and dCl by d alpha. This is what is known as the slope of the moment curve against slope of the lift curve. Basically, moment curve, slope of the moment curve against lift curve, dCm by dl. These are very, if you studied aerodynamics, you will find out that these are the kind of terms used for aerodynamic lift, wing property, etc., etc. The formula for that is, since we are writing it, might as well complete this. This formula for that comes to something like that. And of course, dCl by d alpha we have given already. This term is of course given earlier formula. And now center of pressure, Cp, C bar. Remember, C bar is chord wise, that is what we mentioned here. This distance measured from here, leading edge. You are measuring basically the two coordinate system. You measure the x coordinate from the leading edge, front edge, and the z coordinate or y, if you call, from the top side, that is root side. That is what we call. So this is given as, wait, no, by Cn. Cn of course is available from Cl and Cd. Cn, or rather this we mentioned in last class, and the final thing is Cps equal to 4 by pi bar. Okay. Now this completes my all the required quantities to find out lift, drag, and therefore force and moment. Okay. So this is a more advanced formula that is available today for a particular type of rudder that you can apply. Now, before I go to other thing, I want to tell you about this little bit about this formula for this one, because this formula is going to come later on. That is, see here, this term dCl by d alpha, this one, okay, slope of the lift curve. It turns out there are actually different formulas available for that, depending on the kind. There are two simpler formula for dCl by d alpha at alpha 0. One of them says simply, I will just write it down here, pi by 2 into A per radian. Another formula for that, slightly more advanced, let me write it down. So, if I were to look this three formula, this one, this is the most simple one, I call it 1, this I call it 2, this I call it 3. I will bring back to this three formula. There is a reason for my telling this. It turns out the graph nature looks like that. Here A, here this straight line is, of course, formula 1. Remember, dCl by d alpha is here the first formula provided by Jones. Somebody has given this estimate. It says dCl by d alpha is simply proportional to A. See, this why I am saying, there is an important point. This tells me that if you have aspect ratio low, then you do not get much lift. So, therefore, you do not want to make aspect ratio low. That is why I was trying to tell you about this 1.2, 1.3 aspect ratio. Remember, I will come back to this aspect ratio part. This one, second one, will show a graph which will be going like that. This is 2. That shows like that against A is this 2. And third one, that is this one. This is the one that is the most advanced one, which is been obtained by fitting data on what I should say experimental, much more experimental data fitting. It looks like this is 3. Okay. What you find out at very low aspect ratio, the formula 2 overestimate, because this is formula 2, or maybe we could use color. This is formula 2 and this is 3. See, in low aspect ratio, formula 2, that is this formula, overestimates compared to formula 1. In higher aspect ratio, formula 1 overestimate compared to both of them. Reality is found out that it is more like this, means basically you cannot overestimate it, then you are going to design under design, because you are kind of thinking it will produce so much lift where it does not produce so much lift. So, this is the situation. There is a reason for my telling that, because you see, it tells me that you should not actually have very low aspect ratio. It's not good. What is the physical reason behind that? Suppose you take a rudder like that, flow comes this way. What happens? Water actually may separate out. There is much more three-dimensional effect, much more. Okay. Now, why I mention, in certain bodies, take a torpedo type shape. We are working on that, so I can tell you, you have to have the entire rudder within this limit, because it has to go through a tube. Only place you can do rudder is to have a very long aspect ratio. You see, You don't want to do it, but you have no choice. So what happened? Low aspect ratio wings are not good. What about aircraft? If you see aircraft wings, you know, the aspect ratio is very high, because after all the width direction chord is much smaller compared to the wing. I mean, you have this aircraft with this big wing here, so this compared to this is much smaller, right? You always want to do that, but some of the cases you cannot avoid doing it. And this is also important from one point. Take a ship, which we will discuss next. As I said, I want to estimate the ship's derivatives. The ship's profile is like that, and if you are turning, it is like this ship itself, or rather if I were to see this a two-dimensional case, it is kind of going this way like that. So if you view from this side, that is this plane, it is like a aerofoil or a lifting surface of very low aspect ratio, T by L. So we will find out, as I said, that you can make estimates of hydrodynamic derivatives assuming the ship to be a low aspect ratio lifting surface, and the lifting force that you get, C L, is connected to my y forces. Essentially we will be seeing that later on, we will see that. So that is why low aspect ratio is important, and this discussion I just want to mention these points. Okay, we will have to quickly go to the next 2 points. Now this is CP, what I said. So there are simpler formula for CP, and then we will do a problem quickly. See, there is a simple formula. It says in fact this is actually CPC. This is given by, very simple, sin alpha. Another formula. This is one of formula. And this I will mention about this part. See here what is happening. Suppose what is meant by this open water? You know, there can be rudder, horn type rudder. Remember yesterday I mentioned there is a horn here, and I can have a rudder which is like that. In such case, why I mention this? Because this term, origin for this term, this part of the rudder, this bottom part, this face is facing water directly. So it is, for that CPC for that will be 0.31 C bar being the, whereas for this part which is obstructed or something in front, it will be this. So these are all simple empirical formulas. Okay, fairly simple empirical formula. What we can do is that, depending on the problem, suppose I have to do quickly an estimate, okay, very quickly. Say somebody has given you a rudder, and what happens? You are a designer, you have to design the rudder stock, how thick it will be. You can very quickly estimate the bending stress and the stresses coming on that based on these formulas. If you want more sophistication, obviously you go for the CLCD formula. Okay, means the better formula which uses CLCD's bigger expressions. So it is a very simple thing, really speaking. When you talk of rudder, what I wanted to do was to just mention the possible formulas available. Remember, all of them are ultimately formula to aid a designer. Okay, Now let us say, for example, we will just try to work out a small problem here based on one of the simpler formulas, okay, to find out what is the bending stress on a torque. So there is this rudder given here. I will just work it out from this example. This rudder is a odd shaped rudder. It is, the profile is given something like that, okay, and here these values are given here. This is a stock here 3 meter, this is 1.1 meter, 2.8 in meter 1, and this is the stock, okay. So this here it says this is a rudder here, see the problem was something like that, you know. In fact, these two, the problem says that there is a rudder of, I mean simple problem of this type. This is very not very uncommon for small boats and all, you know, country boat type of thing. Find out what will be the bending stress coming on that point. Yeah, at this point, because it's a you know supported rudder, you are supporting it here, obviously you want to find out how much is the stress coming at. Speed is 20 knots, and obviously the rudder can go up to 35 degree. So obviously the maximum force will come at 35 degree, and it did not say, but I said that okay, in such case what you do, you have to choose one of the formulas, okay. So the formula we use here is 21.1 AR V square dr in Newton as the rudder force. The formula that was the later of the simpler formulas. If you recall that there are 3 simpler formula I gave, this is the later of the one, but simpler than the CLCD form, and Cp is also similarly a simple formula. 0.31 is because we have seen it that it is 0.31 if there is obstruction before, because it is supposed to be a single screw propeller, a ship with one propeller. Now there is a there is some obstruction in front, okay. So anyhow it says that we are just using this value. Now how we proceed AR, actually what we have to do is to do this way. See in these cases we need to do a, how would you proceed? What do we want to find out? Remember, I want to see what is necessary to be found out is the 2 things. One is this location and the force that acts, okay. In fact, you may not want to find the location. What you want to find out is to again moment about this line, moment about this line, and moment about this line, that is T and M, because we can combine them to get M here. That is what I mentioned before. Once again, if you pay attention, why I need to find out the torque coming on this, along this line, that is T, and I need M here. So now I can find Cp, but instead of doing Cp also I can do integration sense. So here I have to do an integration. I have to find out section by section for each one. I will have to find out what is the center of pressure for that 0.31 C formula. Then I can add it all up to find out combined Cp, or for each one I would also know the force, and therefore I can use the formula for force. So what we will do is like this. See here, we will look at this and get back to that. So, here we are calling this to various level, if you call this A, B, C, D, E, then, and these are all 1 meter, I did not mention that, these are all 1 meter. So, you have things like this, let's quickly do chord length, then Simpson's multiplier, then F function of area, then lever, this is to find M, then function of moment, then Cp after bleeding, then Cp aft of bleeding edge. Actually, I will just show you one, and then of course, I have more terms will be Cp of axis and function of torque. I will tell you just one. See, for example, for level A, remember this level A, okay, my total chord length is 4.1 meter, 4.1 meter. This of course, I write 14241 etc., whichever way. This SM. Now, function of area, of course, we will have whatever function of area, this 4.1 etc. Now, lever below stock. See, what we are trying to do, is that lever below stock means we are trying to find out the force, no. So, it is basically Simpson's multiplication. Lever below torque for this 0, because it is 0 meter below torque, this is 1 meter etc. So, this is basically 0. Function of moment is going to be obviously like 0 here. Now, here Cp aft of leading edge, okay. From here aft, how much it is supposed to be? 0.31 times 4.1, okay. That will be 1.27. I just not very clear here, 1.27. What I am trying to say, that you have to do this point by point. Then Cp aft of axis, if it is 1.27 here, then beyond the red line it is 1.27 minus 1.1, that is 0.17. So, this will be 0.17, and of course, the function of torque is going to be obviously this 0.17 times, like that, basically this the force into that part, okay, that is force. Where is that? Okay, this actually is function of torque, because what we are trying to find out is this, that area that comes here, because it is proportional to that into this distance. We are going to be writing there as, that is basically 4.1 into 0.7, 4.1 into 1. This function of torque, right? Okay, with the Simpson's multiplier. Now, what I am trying to say is that ultimately, when you add it all up, you see, then what would happen when you do this? You will end up getting, say, function of area to be, say, here 32.15. So, therefore, area will become h by 3 into 32.5, which will become 10.83 meter cube. Then Cp aft of axis, that will be, when you multiply this function of torque, this part, okay, this part which turns out to be 5.37, will become 5.37 by area 32.5. See, what I am saying here, I tell you, this is, you are trying to find out centroid of this point, okay. You are trying to find out here where this point will occur. Now, what you are doing, you are trying to take the formula for the forces coming and the Cp for that individual one. Obviously, if there is so much force coming at this, so much force coming at this, so you are adding this up to find the net moment, divide by that, you get Cp. So, that is what you are getting, you get this Cp aft. Then Cp below stock, this will be when you take this function of moment, because what you are doing is here again, each force multiply the distance, each force multiply the distance. So, that gives you the net force moment about this. So, when you do that, you end up getting this, that moment. If I do that, this is basically this part, Fm, this part. In this problem 48.8 by something like, let me see this, you will end up getting 1.502 meter. So, what we end up getting is that something like this, that this point is a distance of 0.165 and this distance turn out to be 1.502. That is what you end up getting the center just by using this formula. And then having done that, what we can do is to find out the total bending moment or combined bending moment. Now, first of all, BA at stock, that is M. This is going to be, well, before that the force on rudder, before that we can write FR. This is 21, what is the formula? 21.1 into, see here, yeah, A will do, AR, yeah, this is 10.83 multiplied by V. V is 20 naught into, well, 0.5144, if I do square, into delta R is this. AR, and this is the constant. That many newtons, this will turn out to be 1.272, no, it is turned out to be 84. Have a look at this number, 847 kilonewton. How many tons equivalent approximately? Yeah, so around 84, 85 tons. So, this is the kind of like force coming, remember. So, you see why I am saying that, have a kind of a feeling about the kind of numbers we get. 85 tons is not a very small force. If you consider it, average commercial car weighs 1 ton, it is like 85 weight of 85 cars, right. So, in ships everything is quite big, and this size is only 4 meter by about 4 meter, right, 16 meter square. 4 meter is 12 feet, it's a huge plate, all right, but look at the force that is coming. So, what do you think the stock you have to made of? That is what we are coming at. Okay, let us look at bending moment. About the stock, this is going to be 847000 into 1.502, because that is what the distance is, isn't it. So, here I have got 847 kilonewton into 1.502, that is my bending moment M. So, this turns out to be equal to 1.272 mega Newton meter. Then torque, yeah, torque is coming to be same 847000 into 0.165, that will give you 140 Newton meter. That is the torque coming here, torque on this, bending moment on this. So, you end up getting equivalent bending moment half of m plus square root of m square plus t square equal to 1.276 mega Newton meter. So, the stress, now here actually this, if you want to, now this now actually this problem, the stock Z is also given, I believe, section modulus this 1.276 now. See the stress 12.76 mega Newton per meter square. if you compare, you will find out that you actually need very strong, like this stress, you cannot have wooden stock or something. You need solid. See, so this problem is very simple. What I did try to do quickly, but essentially what I mean is that this will give an idea regarding the kind of stresses that will come on your stock. You can be off by say 10%, 20% depending on what formula you use, but for design purpose it is good enough initially. And these kind of numbers should give you a feel of the kind of stresses that we deal with even in rudder stock and rudder force. So this is the just a simple example. So anyhow, I will end it here today, and we will see next how we can talk little bit about some empirical formula for hull derivatives. We talked about experiment, but certain formula. With that, I will end it today.